Hi mathematicians, I'm going to go ahead and try to help out with an eigenvector, eigenvalue solution for a system of homogeneous diffie-q's along with the phase plot, in hopes that this is going to help you out with your homework and maybe your life. Who knows? Okay, so suppose I have this system, right? I know it's a system because I have two equations. And so what does this mean on the left-hand side? Well, this is just the first derivative of x, right? x1. And this is the first derivative of x2 here, right? And so then we have x1 plus 2x2, x2 prime equals 3x1 plus 2x2. And so again, and I know, we're almost to the end of the semester, but these x's represent equations, right? Some kind of function is what we're looking for here. And so instead of in algebra solving for a point, we are now solving for a whole equation. So I just want to remind us this. These are homogeneous equations because we don't have them like equaling something weird, right? So let's go ahead, and the first step is we're going to write in matrix form. And I know not everyone has had linear algebra at this point, but I feel pretty confident that we all know what a matrix is. So how do we then change this equation into a matrix? Well, I'm just going to say that my x1 prime, x2 prime, we kind of turn it into like a vector, right? Anytime that your matrix is one-dimensional, meaning it is just a column or just a row, it is considered a vector. Equals, and then this first column is going to represent all of my x1s. So who are my x1s? Well, I have an invisible 1 here. We'll put that there. And then I have this 3. And then here we have a 2 and a 2 representing my x2s. Okay? And then we're going to go ahead and multiply that by our vector x. Okay? And so let's go ahead and solve using eigenvalues, eigenvectors. Okay, and again, this is not something that your book really emphasizes, but I think this is actually one of the more important things, especially if you are an engineering major. I feel like you're going to see this again, and I am saying this because I have engineering degrees and I feel like this is what they made me do in school. Okay, so again, the first thing we do is change it to matrix form, and then we're going to go ahead and subtract our eigenvalue along the diagonal, okay? The diagonal of the matrix being everything, like this. And you can do this with a larger system, but it gets crazy, and we're not gonna do that. And so on the left-hand side, actually what we're doing is we're saying the determinant of A being our matrix, minus lambda times the identity equals this. What is, Beth, you're saying a whole bunch of words. I don't know what any of them mean. Don't worry about it, okay? For now, as long as you know that you go from here to subtracting this eigenvalue along the matrix, that's okay. Okay, like you can deal with determinants and identity functions in linear algebra. If you do know what an identity function is, then you know that here I am just multiplying that identity by this lambda to get this along the diagonal. Okay, from here, next thing we do is we do what's called finding the determinant. And to do that, I'm going to multiply this times this. These two guys are going to multiply together. And then I'm going to subtract that times that. Okay, so what do we get? So I get a 1 minus lambda times 2 minus lambda minus 6. Okay, and so I hope you see that. See that there. And so let's find out, oh, let's make a little equal sign here. And so let's figure out what this is. So I'm going to go ahead and FOIL this out. Right? If it helps you, make your little arrows. All right? I've been doing this longer than you've been alive, and I'm making arrows. 1 times 2 is 2. 1 times minus lambda, negative lambda times 2, negative 2 lambda. Negative lambda times negative lambda is plus lambda squared minus 6. Let's go ahead and clean this all up. And we get lambda squared minus 3 lambda minus 4. Okay? So again, I know this seems very, very strange, especially if those of us who have not taken linear algebra, but we started with this equation here up on top, or these equations, right? Here's our system. And we just translated that system into this matrix. After we translate into this matrix, we write minus lambda along the diagonal. We find what's called the determinant. To do that, we multiply this diagonal together and put that first. And then we subtract, I don't know if you can see it anymore, but this is a minus right here. Right? We subtract the multiplication of the other diagonal. I just clean that up, and I get a nice quadratic. And so I am going to do what we love doing with quadratics, is I'm going to factor this. And so what does this become? Of course, it becomes lambda plus 1 and lambda minus 4. And so then we have our two eigenvalues. Our first eigenvalue, lambda 1, is negative 1. And our lambda 2 equals 4. Okay. And so then now, so I have these. Next, we need to find the eigenvectors. Okay, let's see if this works. What if I put that over there? Can we see both pieces of paper at the same time? Maybe. I think so. There. Okay, we'll see. We'll see if this helps, because I like to be able to see. I wish I had a board here. Right? I'm running out of board space. Okay, here we go. So next we need to find the eigenvectors. So let's find the eigenvector minus 1 first. Okay, so what I'm going to do is let's go back and we're going to rewrite our matrix. So my matrix is 1, 2, 3, 2. And what I'm really interested in is what is 1 minus lambda, or the matrix with 1 minus lambda, 2 minus lambda. We're just subtracting along the diagonal. And then I'm multiplying this by n1, n2, and this equals 0. Okay, this is the part, it's homogeneous, right? Or it's a milk equation. Right? Because we don't have extra stuff. I'm not telling you that it equaled like some weird function over here. Right? Remember before when we're solving homogeneous versus non-homogeneous equations, and that actually usually means what we're talking about on the right-hand side. But I digress. So here we are, and so what are we trying to do is we're now trying to find a vector, right? So we go 1 minus, that corresponds to this eigenvalue. 1 minus minus 1, 2, 3, 2 minus minus 1. Again, I'm going through a lot of steps here and showing a lot of work because I want to make sure I get the right answer. Okay, when you feel more comfortable, absolutely skip steps because I do. 2 equals 0, 0. Okay. You just need to do this once. You should always end up with the same values here or the same relationship here, regardless of whether you're going to multiply this times this or if you're going to use this one. Okay, you can use either row. You don't have to use both rows. Either row. Okay, I'm going to use row 1. And so what do I know then? What does row 1 tell me? 2 times n1, 2 times n1 plus 2 times n2 equals 0. Oh, I forgot my 2 here. Go ahead and solve and create a relationship between n1 and n2. That's what we're looking for, is this relationship between n1 and n2 that's going to tell us what our vector looks like. So if I go ahead and divide both sides here, I get n1 equals negative n2. And so we're going to go that the vector associated with, I'm going to put negative 1 here. You might see, some people might put 1 like this is the first one. I'm going to put this little negative 1 to say this, it's corresponding to the negative 1 eigenvalue, is what I'm trying to note myself. And so I can pick whatever numbers I want in here. We're going to n1. n1 equals negative n2. So we're going to make this, actually, I don't want to confuse you guys. Okay, let me do this again. Okay, so I have n1, and then what is n2 in terms of n1? So if I solve for n2, I get a negative n1. Another way to think about this is whatever n1 is, n2 is the opposite. However you make sense of this relationship right here, you have to recreate that relationship here. This is recreated with symbols. What does it look like with numbers? The eigenvector that corresponds, with the eigenvalue of negative 1 can be 1, negative 1. Okay? Can you pick different numbers? Can you have 5, negative 5? Yes. Could you have 100, negative 100? Yes. Could you have a negative 100, 100? Yes. These just need to be opposite signs and the same value. Does that make sense? I hope so. Okay, so that's our eigenvector for our negative 1. Let's go ahead and find our eigenvector for our 4. Is it 4? It is 4. Okay. So find eigenvector for lambda equals 4. Lambda 2 equals 4. Okay, and so what am I doing here? Let's go ahead and go back to our original matrix. And now I'm going to subtract lambda along the diagonal. And so this becomes 1 minus 4, 2, 3, 2 minus 4. You can see I'm being kind of bad here. I'm not including all the details, right? I should have that written there. We're multiplying. Yeah, I got a whole bunch of stuff I'm really not doing. But that's okay. All right. So I'm subtracting 4 here. What do I get? I get minus 3, 2, 3, minus 2. Again, we're trying to find our eigenvector. So I'm just going to go ahead and set this up. And again, you can use the top row or the bottom row. It doesn't matter. Okay? I'm going to multiply these together using the top row. I get negative 3n1 plus 2n2 equals 0. Again, I'm trying to create a relationship between n1 and n2. I get negative 3n1 equals 2n2. So I get n2 equals negative 3/2 n1. So my vector n1 negative 3/2 n1. How do you feel about that? Okay, and so what are you going to pick for numbers? What are you going to pick? What are you going to pick? You can pick this any way you want. Did I do that correctly? No, you know why? What am I missing? Did anyone catch it? That should be a negative. This should be a positive. There we go. That's fixed. Okay, so you can pick any number for n1. What are you going to pick? Some of you are like, I'm picking 1. You know what I'm picking? I'm picking 2. And I'm using the eigenvector 2, 3. Does that make sense? Right? So we have here my eigenvector for, we'll use an n, and then we'll put a 4. Very messy, I know. Okay, so let's go ahead and write the solution. We're ready, we're ready, we're ready. Okay, so we have xt equals c1 e to the negative t. Where did I get that? Where did I get negative t? First eigenvalue, negative 1, right? That's where I got that, okay? And then I'm going to go ahead and multiply it by my eigenvector that corresponds, what was my eigenvector that corresponds? 1, negative 1, okay? So I do 1, negative 1, plus C2e to the 4t. Again, where did I get that 4? That 4 was my second eigenvalue. Okay, and then what's my vector here? 2, 3. Okay, how do I draw the phase plot? Okay, phase plot. We have a 1, negative 1. What does that look like? What does that mean? Where is that? 1, negative 1. Right? I'm going to go, and I don't know if you, but I do this all the time, just little sketches. Right? It doesn't have to be exact. You know, I'm just giving you an idea, and that's like, I'll expect for you for your assignment too. You can just do a hand-drawn graph if you want. Okay? 1, pardon me, negative 1 gives me a dot here. And then what I do is I draw a line through the origin using that dot. Okay? Now, this corresponds to this portion right here, right? Do you see how this is a negative? Anything to the negative power, it's becoming smaller and smaller and smaller and smaller, right? So what I know is I know that this vector, everything along this is going to be pointing in. Does that make sense? I hope so. Okay, in towards the origin. Now let's go ahead and do the other one. The other one's going to be 2 over and 1, 2, 3 up. Let's go ahead, draw our vector. Now this, however, oh, look at, I found a See, this is my -1. Make that blue. And let's see what else I have here. Pink. Is pink going to make it? I guess pink's going to do it. Okay, and then we have this 4 here, right? That's going to be this guy. All right? Because 4 is positive, these arrows are going to go out. Okay, and so what we have here, we have what's called a saddle. And so we have to think about the direction that these are gonna kind of flow. Okay, and so this will come more later, like when you have more experience with this. But for right now, it's good enough to realize that this is going to come in this way and then go out this way. It's going to come in this way and go out this way. It's going to come in this way and go out this way. Should be a little bit tighter to that blue, but that's okay. And go out this way. And are my lines perfect? No, they're not perfect. I'm not perfect. I'm not a robot, right? But do you see how they're going? Let me draw some arrows. Right? We're going in this direction and then we're flowing out. Okay? And then one more let's do over here, in here, and then we're going to go parallel that way. And maybe one more. Okay, so that is an example of one eigenvalue, eigenvector solution. Okay, I hope it's helpful. For the homework assignment, you aren't making a video, you're just writing up your solution. And then writing up your phase plot and then giving me a couple sentences about, your phase plot and how you knew it was going the way it was going. All right. Again, I hope this was helpful. Thanks.